Okay, in this video, we're going to quickly go over section 5.3, which is all about the integrated rate law and different from how we solve all of our differential rate law problems. So here we go. Okay, so if you remember in our differential rate law section of notes, we were given a data table. It had concentrations and it had rate information. With the integrated rate law, we're going to be given a different chart of data. So we'll be given concentration values and we'll be given how that concentration changes over time. So our charts are going to look a little bit simpler. There's only going to be two data points, and that's what we're going to be looking at, is how that concentration changes over time. And if we're given this data instead of what we used last time, our process for solving these problems and figuring out the order of the reaction and all of that is going to be different. So our integrated rate law is going to be used for decomposition reactions only, where we have a certain reactant that is going to break apart into different products. And so here's what we're going to do. Basically, we need to create 3 different graphs. And we need to figure out which of those 3 graphs gives us a straight line. And whichever one gives us a straight line is going to tell us the order of the reaction. So if the reaction is a 0 order reaction, when we graph the concentration versus time, if that gives us a straight line that looks like this graph over here on the right, then that would be a 0 order reaction. Now, as far as equations, we would still write the rate law equation the same way that we did before. So we would have, rate equals K times the concentration to the 0 power, which that goes away. So my rate law equation would still be rate equals K. But my integrated rate law equation is going to be something different. So the equation that you guys see down here in green, this is going to be what my integrated rate law equation is going to be. Now, on your reference sheets, these equations are going to be given, but they're not going to tell you which order they go to. So basically, the one with concentration, that's going to be my 0 order reaction. What I want you guys to notice is, since we're dealing with graphs that are going to give us hopefully a straight line, or whichever one gives us a straight line, the format of this equation is just the same as the format of any straight line graph, which is just, sorry, bell's ringing, which is just y equals mx plus b. So the reason why that's important is because when we go later to solve for the rate constant k, that's going to be the absolute value of my slope. So if we have 3 different graphs and we find the one that gives us a straight line, if I can find the slope of that graph and I absolute value that slope, that's going to give me my rate constant value. For my first order reactions, if I plot the natural log of the concentration. So natural log, yes, we're going to use that in here. We need to natural log value the concentrations. Really, you just need to be able to find the natural log button on your calculator. If I take the natural log of the concentration values and I plot that versus time, if it gives me a straight line, like the graph that I see over here, then that's going to be a first order reaction. And again, my integrated rate law equation, IRL, integrated rate law equation, is going to look like this one that I have here in green. In the same format of a straight line equation, y equals mx plus b, my k value is still going to be the absolute value of the slope of my graph, my straight line graph. My regular rate law equation is just going to be rate equals k times my concentration to the first power, because it's a first order reaction. The only other thing that we need with first order reactions is a half-life equation. So if we have a first order reaction, we could be asked to find half-life values. So half-life is probably something that you've heard of. So half-life is going to be the time required to reach one half of the original concentration. So how long does it take to get cut in half? That equation also given to you, but half-life is going to equal 0.693 divided by K. 0.693 is just the natural log of 2. There's some calculus deriving of these equations. You don't need to worry about that too much as long as you guys can use these equations properly. All right, next one, second order. If I take 1 over my concentration values and I plot that versus time, if that gives me a straight line like the graph over here, then it would be a second order reaction. So again, remember the goal is going to be basically to create 3 different graphs and figure out which one is the straight line, and it'll tell me the order of the reaction. So my equation for the integrated rate law is going to be 1 over the concentration equals KT. Notice that the slope of this graph is a positive slope. My other 2 graphs had negative slopes. That's because I'm inversing the concentration. Concentrations are going to be decreasing over time for my reactants, but if I do 1 over that value, then they're going to be increasing. And then this right here, anytime we see that next to anything, that represents our initial concentration at time 0. Okay, so that one would give, if it gives us a straight line, would be second order. And we've talked about this already. The absolute value of my slope would equal K. My regular rate law equation would be rate equals K times my concentration squared because it's second order. Okay, so here's what an integrated rate law problem is going to look like. Basically, we'll be given the overall reaction. So I've got 2N2O5, and then it's decomposing. They're all decomposition reactions into NO2 and oxygen. And I'm going to be given 2 sets of data points. So I've got time here in seconds. And remember, my goal is going to be to analyze 3 different graphs. And so if I'm analyzing 3 different graphs, time is going to be the x-axis for all 3 of my graphs. And then one of my graphs is going to be my concentration. Now, all of these little boxes I gave you is just for us to be able to fill in different things. I need to go ahead and I need to calculate the natural log of all of those concentrations. I need to calculate 1 over the concentration for all of those. My natural log would be, those points would be my y values for my second graph, and then my 1 over concentration values would be my y values for my third graph. Okay, so if I natural log all of these values, when I natural log 0.1, that's going to give me negative 2.3. Natural logging 0.0707, I get negative 2.65, and then I get negative 3, and then negative 3.69. Usually, 4 points is going to be enough for us to be able to figure out what our graphs look like. So we'll go ahead and stop there. For my 1 over concentration, 1 over 0.1, that's 10. 1 over 0.0707 is 14.14. 1 over 0.05 is 20. 1 over 0.025 is 40. Okay, so I've got all these points. Now, technically, so we did this. We calculated the natural log. We calculated 1 over the concentration. Technically, what we want to do next is we want to analyze 3 different graphs. Okay, so I would have, what is my concentration versus time look like? What does the natural log of my concentration versus time look like? And what is 1 over my concentration versus time? What do those graphs look graphs look like and which one gives me the straight line. If this one gives me the straight line, then it's 0 order. This would be first order. This one would be second order. Now, instead of having to draw all 3 graphs, I'm going to show you a little shortcut for figuring out which graph gives you the straight line. We can go ahead instead and calculate slope values. And when I calculate my slope values for each data point, I'm going to go ahead and take, so let's go ahead and do my concentration versus time. So my Y2 value would be 0.0707. My Y1 value would be 0.1. And my X values would be 50 minus 0. And I would go ahead and I would calculate what that slope value is. When I calculate that, I get negative, oh gosh, this is going to be small, sorry, 5.86. I'm just going to put a little e there instead of times 10 to the negative 4. So 5.86 times 10 to the negative 4. Then I'm going to go ahead and I'm going to do it for the next 2 points. So 0.05 minus 0.07 divided by 100 minus 50. That gives me negative 4.14 times 10 to the negative 4th. Okay, so right away, I can just tell that those 2 slopes aren't the same. Remember, we're looking for the graph that gives us a straight line. And if it gives us a straight line, it means that the slope is going to be consistent from one point to the next. So that's probably not going to be the case. So now I'm going to go over to my natural log graph, and I'm going to find the slope between these 2 points. Negative 2.65 minus negative 2.3 divided by, these are still my x points, 50 and 0. That gives me negative 7 times 10 to the negative 3rd. I'm going to do my slope between these 2 points. I get negative 7 times 10 to the negative 3rd. The slope between these 2 points, negative 7 times 10 to the negative 3rd. They don't always work out perfectly. This particular one, they get pretty close. Sometimes you need to calculate a couple more slope points just to be sure. But this one, I can pretty much tell that this is going to be the graph that gives me a straight line, which means if it's a natural log graph, then this is going to be a first order reaction. And if you want to go through and double check, you could calculate these slopes. You'd get 0.08. Here you'd get 0.12. So those are different. I don't need to calculate any more slopes. But if you do, you could go ahead and do that. Okay, so if it's first order, because my natural log graph gives me the straight line, then I can go ahead and absolute value the slope. Now, if you're going to figure out the slope, you do need to do the last point. So like if I natural log all of my data points, 1, 2, 3, 4, 5, 6 data points, that's this one down at the bottom is negative 5.08. The most accurate value for your K is going to be using your last value and your first value on your graph. So I want to use negative 5.08 minus negative 2.3. And then go ahead and divide by 400 minus 0. Okay, that's going to give me 6.95 times 10 to the negative 3rd. And if it's first order, my units still apply. For my K value, it's 1 over seconds, or S minus 1. If I want to go ahead and write out my rate laws, my rate law equation is just going to be rate equals K times, and then I'm going to go ahead and plug in my N205 and to the first power because it's first order, but we don't have to write ones. If I want to write out my integrated rate law equation, then I'll go back to what we had on the previous page and use that format where I have the natural log of N205 equals negative KT plus my initial concentration of N2O5. Okay, so now we're going to go ahead and do some application of, once we know what the order of the reaction is, how can I use that to solve different problems? Okay, so in this example, it says we've got a first order reaction. So read carefully, because sometimes they tell you what it is, and automatically I know that this is going to be the equation that I use, where I have the natural log of the concentration equals negative KT plus the natural log of the initial concentration. So once you know the order, then we can use those integrated rate law equations to solve for lots of different things. K values, the time it takes for concentration to go down to a certain amount, the initial concentration, final concentrations, all of that. Okay, so it says a first order reaction is 38.5% complete. What that means is that if I start with 100% and it's 38.5% complete, that means I have 61.5% left. And it says it takes 480 seconds to get to 61.5% left. Calculate the rate constant. So when I plug into this equation, I can plug in actual concentrations here. I can also plug in percentages. So my initial concentration was 100%. My final concentration is 61.5. So I'm going to go ahead and say the natural log of 61.5 equals negative K. And my time, because the question is asking us to solve for the rate constant, which is K. The time is 480 seconds. So that can get plugged in there. And then plus the natural log of 100. Okay, from there, we're solving for K. Natural log of 61.5 is 4.12 equals negative 480K. I just kind of rearranged that there. And then the natural log of 100 is 4.61. Okay, algebraically, we can go ahead and solve for K. K is going to be 1 times 10 to the negative 3. And it's first order, so it's S minus 1. Okay, second part of the question. There's 4 parts to this. Calculate the half-life. Half-life equation is given to you, 0.693 over K. I can go ahead and take my K value from my previous section, plug that in, and get 693 seconds, which means it takes 693 seconds for that concentration to go from 100% to 50%. All right, letter C, how long? How long is time? How long will it take for the reaction to go to 95% complete? 95% complete means I have 5% left. I have my K value from the previous part, 0.001 times time, plus the natural log of my original concentration in percentages would be 100. Natural log of 5 is 1.6, and then I get negative 0.001 t. Natural log of 100 is 4.61. Solving for time, I get 3,010 seconds. I think that's rounded to significant figures, maybe. All right, last one, part D. If the initial concentration is 0.8, what will the concentration be after 960 seconds? So this equation, more specifically, this concentration is what is my concentration after a certain amount of time. So I'm solving for this number, basically. And I've got my K value, 0.001, and time is 960 seconds. All of these problems, by the way, since they told me that it was first order, I can use the same first order integrated rate law equation for all of them. And then natural log, my initial concentration is 0.8. So this time I actually have molarity values to plug in, so I can just go ahead and put that directly in here. All right, when I plug in everything over here on the right, let's see, this is going to give me negative 0.96. This gives me negative 0.223. So then I get the natural log of x equals, when I add those together, I get negative 1.183. Okay, so I added this one into our examples because we need to talk about how do you solve for x when it's attached to a natural log. So if you have done this in your math class, some of you have, some of you haven't, wherever your natural log button is on your calculator, right above that as a second function is your inverse of your natural log. So if I want to go ahead and solve for x, I'm going to find that button and I'm going to find it as my second function. E is the value that is the inverse of x. So then you can go ahead and do e to the negative 1.183 power and solve for that x value, which is going to give me my concentration after 960 seconds. So it's 0.306. All right, that is it for 5.3, you guys. Hopefully that was pretty quick. Hopefully it makes sense. We'll be doing practice with this in class tomorrow. So I will see you then. Have a great night.